Thanks, Ashley. Good afternoon from LI-COR Biosciences here in Lincoln, Nebraska. It's nice to see so many people joining our webinar today. As Ashley mentioned, today we'll be talking about the new LI-7700 Open Path Methane Analyzer. We really designed this instrument for atmospheric measurements and Eeddy Covariance measurements in particular. And today we'll go ahead and talk about some areas where methane is of interest to researchers right now and some things that are currently going on related to methane research. We'll introduce the LI-7700 instrument, and then we'll show some data that we've collected with that instrument in the field and talk about how it can be used in a lot of different areas for a lot of different kinds of measurements. To kind of get things started, we've got a little bit of information that we'd like to just make sure everyone's aware of to kind of help get the discussion started. And this chart is from the 2007 IPCC report. It shows the relative forcing of different gases in the atmosphere. CO2 is, of course, the most well-known greenhouse gas in the atmosphere, but methane is also an important greenhouse gas. It's present in the atmosphere in much smaller concentrations, but it's actually 23 times as strong on a molecule per molecule basis at forcing climate. Methane is important because it is released from wetlands, and there's also a very large amount of methane stored in permafrost. And so as climate does warm and permafrost continues to melt, more and more methane will be released into the atmosphere. So we want to make sure that we understand that and kind of have an idea of what's going to be happening as that continues on. Now, this next chart is again from the IPCC report, and it just shows the growth trend of three main greenhouse gases. The red line is carbon dioxide, the blue line is methane, and the black line is nitrous oxide. And you'll see that for many, many years those gases were all relatively stable in concentration in the atmosphere, and then there's a significant increase in more recent times of all three of those gases, and much of that is attributed to human activities as we entered the industrial era and as we continue to produce greenhouse gases through anthropogenic sources. Okay, this next slide shows a compilation of data that's been collected to kind of just zoom in on more modern times. On the top here we see the atmospheric concentrations of methane since the 80s through about 2006, and we see that that's continued to rise, but appears to be kind of reaching more of a steady state. And then below we see the relative growth rate year to year. So we see that there's a lot of variation from year to year in that rate, and we also see that while the rate does seem to be declining, it's been positive for the majority of this time. So the concentrations in the atmosphere are continuing to rise, just not as rapidly as they were maybe 20 years ago or so. So it's important for us to be able to monitor atmospheric concentrations of methane effectively, because there is so much variation from year to year, and we're still not sure where this is going. There's a variety of questions that scientists are currently evaluating and trying to answer related to atmospheric methane. We want to know more about the sources and the sinks of methane. We want to know what factors regulate the strength of those sources and sinks. And we also want to know the impact of the change in atmospheric methane concentration on climate. So those are three main questions that people are working through right now, and we've got varying degrees of understanding there in all of them. This chart just shows a brief breakdown of our current understanding of the methane sources. You'll see a large portion, 22%, is coming from wetlands, 21% from rice fields, about 15% from domestic animal production, and then there's a variety of other sources as well. And so we need to, again, just continue to characterize these sources and better understand how they're interacting with the atmosphere and with the climate. So currently there's a variety of types of instrumentation that people can use to measure atmospheric methane concentrations. Traditional methods would include gas chromatographs or mass spectrometers. So in cases like that, you'd go out in the field and typically place a chamber on the ground if you're looking at fluxes from the soil, or you'd collect an air sample from the air, and then you go ahead and take it back to the lab, run it through the gas chromatograph or the mass spec, and get your methane information that way. So those instruments are good. They're very precise and accurate, but that's a pretty time-consuming method, and it's relatively expensive, and you just can't get regular high-frequency data collection because you have to go out, collect a sample, go back and analyze it. So it's not ideal for long-term studies and high-frequency studies. More recently, closed-path gas analyzers have become available that can be taken into the field and deployed, and that allows you to get more regular data collection, and it allows you to collect that data with a little bit less time, so you don't have to go out and collect those samples as frequently. But the instruments that have been available to date tend to be really designed for laboratory use, and you can use them in the field, but it can be relatively difficult to get everything put together and to maintain those instruments for use in the field. They tend to be expensive and just kind of difficult and cumbersome for field research. So there hasn't been a really good way to make atmospheric methane measurements in the past, and now we've got a new opportunity and a new instrument that people can use for that. It's the LI7700 Open Path Methane Analyzer, and here's a picture of it. The LI7700 is a high-speed, high-precision methane analyzer that was designed for making continuous measurements in the field. It has 5 part per billion resolution at 10 Hertz, and it has user-selectable bandwidth of up to 40 Hertz. So it's a very precise and very high-speed instrument that's really ideal for deployment in the field. It weighs about 11.5 pounds, and so it's pretty easy to get out and get installed in the field. And then one of the most important characteristics of the instrument is its low power consumption. The 7700 requires only 8 watts of power during normal operation, so it can be deployed almost anywhere with a solar panel power source, and that's a pretty significant advantage is to be able to put instrumentation in remote areas where there's not access to AC power. The instrument has Ethernet communication, and it also has optional high-speed data logging, so you can collect methane and wind speed data locally with the instrument, and you can also transfer that data over a network if you have a network connection to your site. The 77 has self-cleaning optics, and it has temperature-controlled mirrors, so we provide more complete data sets in difficult environments where maybe in the past instrumentation would have had a hard time collecting data continuously. We've made several advances with the 7700 that make it more robust in difficult environments. And we really designed this instrument so it could be deployed nearly anywhere and then left unattended for data collection for long periods. We'll talk more about some of the instrument details later on in the presentation, but first I want to provide a brief overview of the instrument and how it works, just so we have some background as we move forward. So the LI7700 is a Harriet cell optical configuration, and you can see a CAD drawing of that here on the screen. At the top we have an optical source and a detector. There's a mirror here, and there's a mirror at the bottom, and these red lines in this CAD drawing represent the laser path. Now there's an infrared laser source in the instrument, so you can't actually see it, but this is just a representation to give people an understanding of what the path looks like. So we've got these 2 spherical mirrors that make up the Harriet cell, and they're placed half a meter apart, but they have 60 passes of the laser. So our total path length, our total optical path length for the instrument is 30 meters, and that gives us a real high resolution for methane concentrations. And traditional LI-COR analyzers would not have mirrors. They would have a single pass optic where you've got a source at one end, a detector at the other end, and that's all you need. With methane, we need a multi-pass cell because there's such a small concentration of methane in the atmosphere, and the absorption signature that we're looking at is so small that we need to get more path so that we can increase the absorptance to a level that we can measure accurately and with the lowest amount of noise possible. So that's a general idea of what's going on with the instrument. And as I mentioned, traditional instruments have a single pass optic, and just to refresh people, with NDIR technology, many of you have used LI-COR gas analyzers in the past or are currently using them, so you're familiar with with drawings like this where we've got an optical source at one end, a detector at the other end, and we pass infrared light through the cell. We stream air through the cell, and we measure the absorption of that infrared light at a particular wavelength that we can then use to measure concentration of the absorbing gas in the cell. So just another look at how NDIR works. Here's a chart of absorption and wave numbers, and you'll see that there's a band of wavelengths here that the CO2 analyzers can see and sense. And so with a broad source, we shine infrared light through the cell, and we hit a variety of absorption bands for CO2, and then we filter our detector very specifically to be able to get absorption that's just related to CO2 or water vapor, but it's a broad band absorption. So the principle of measurement with the LI7700 is wavelength modulation spectroscopy. So it's a different method. And the way wavelength modulation spectroscopy works, we're going to talk about just a little bit here, and we'll have more opportunity to learn about that in the future. The LI7700 uses a single mode tunable near-infrared laser source, and it operates at ambient temperature. So using that laser source and wavelength modulation spectroscopy, we scan the laser across a single methane absorption feature that's near 1.6 microns. So we make this scan with high resolution and a high repetition rate. We just keep scanning back and forth over this single absorption feature. And while we're scanning across the feature, we also modulate the wavelength of the laser at the same time. So we're scanning and we're modulating, as this image shows, at the same time. And what that does is it almost eliminates the 1/f noise from the laser source, and it also allows us to detect absorptions that are smaller than 10 to the -5. So through this WMS process, we can resolve a very small actual absorption feature in a way that gives us a bigger signal, so we can have a better measurement with a shorter optical path and a higher resolution. So once we've made these scans, we demodulate the output signal at twice the modulation frequency, and that gives us a line shape that looks kind of like this. This is just an example here, and then what we do is we compare the line shape that we collected from our sample with a reference line to determine the methane concentration. So the amount of fit between the sample line shape and the reference line shape is proportional to the density of methane, and that's how we make that measurement. Now, pressure and temperature can both cause changes to the line shape that we're measuring. Laser power and mirror reflectivity can also be affected by changes in pressure and temperature. So we have to measure those in the instrument and compensate for these changes in software. And we do that through a thermocouple that's very near the optical path that we're measuring, and a pressure sensor that's embedded in the instrument. Now, as I mentioned, there's going to be an opportunity to learn quite a bit more about wavelength modulation spectroscopy. The next webinar that we have will be focused on that topic. We're going to have Brad Renchie, who's a design engineer at LI-COR, come in and talk through wavelength modulation spectroscopy, how it works, and how it's been implemented in the LI7700. So if you're interested more in the details of how we actually make the fundamental measurements in this instrument, please make sure that you come back in 2 weeks for that webinar as well. Brad will have a lot more to say about that topic. In the meantime, I can tell you about some of the technical advantages of using wavelength modulation spectroscopy. The reason that we went with this approach is that this technique makes the instrument insensitive to baseline laser power. So that's because we're detecting the second derivative of the signal, and that's really important because lasers are going to age, their output is going to change with temperature and with time, and we need to be able to account for that in some way. Other measurement techniques make it susceptible to those small changes, and so those instruments have to monitor them very closely and compensate for them. But with wavelength modulation spectroscopy, that laser power is just canceled right out of the equation, and it's not a concern for us. Also, the WMS gives us an opportunity to make the measurement with a relatively short path length. 30 meters sounds like a lot compared to the 12 centimeters you're used to with a 7500, but 30 meters is actually considerably shorter path length than most methane analyzers. Traditional analyzers that are currently available on the market might have kilometers of path length. what's important about that difference is that for a 30-meter path length, the LI-7700 can give similar resolution to other instruments that have kilometers of path length. And with kilometers of path length comes the need for very highly reflective optics and very precise optical alignment. And it can be very difficult in a field-based instrument to really maintain the optical performance when there are such stringent requirements. With WMS, again, in a short 30-meter path length, we can have a lot more flexibility in how clean the optics are, how well aligned the optics are, and still get a very high performance instrument. One of the other technical advantages of WMS is that we don't have vacuum pumps, and that's really important in field instruments because of power consumption and pressure changes. Because to operate an instrument at a high enough flow rate to get Eeddy covariance measurements made in a closed path setting, you need a very high power consumption vacuum pump. So the open path analyzer gets away from that and really makes the instrument a lot more field ready. So those are some of the things that are important about WMS and how it's implemented in the instrument. But like I said, there's a lot more there that you can hear about in a couple of weeks. So just a few performance charts from testing that we've done with the LI-7700 in the field here. First, I'll show you the linearity of the instrument. This represents concentrations measured at 5 different points. With this particular instrument, you'll see that the calibration is very linear. The R squared here is 0.99998, so a very linear instrument, and that's part of having a laser source and having the optics designed the way they are. So we know that once we get the instrument calibrated, we have a very good fit between the points that we check. The next chart that we'll look at is absolute accuracy of the instrument. You'll see here a percent error chart that shows very near zero across concentrations that go from ambient to well above ambient. So you'll see that the instrument is very accurate. And the third chart that I'll show you here is an RMS noise. And again, this one was collected at 1 hertz. So 1 sample per second. You'll see that the noise in parts per billion is less than 2 parts per billion from 0 to 10 parts per million concentration. So again, you'll see that the instrument is very stable and that it has very low noise and high resolution. So those are some important key things to consider about instrumentation as you look at making atmospheric measurements. Now we've got a poll, and we'd like to get a little bit more of a sense for what our listeners today are doing currently in the field. So the question is, are you currently measuring ecosystem methane fluxes? And we've got a variety of answers here that we'd like you to consider, and we'll take just a moment to let you go ahead and get your answer entered in, and then we'll continue on from here with the rest of the talk. Okay, thanks everybody for giving us those responses. It's always good to know what people are currently doing and what you're planning to do in the future so that we can better tailor our talks and also tailor our instrumentation to what people really need in the field. So thanks for giving us that information. And what we're going to talk about next is just a little bit of information about Eeddy Covariance, because again, this instrument was designed with Eeddy Covariance in mind. We want to make sure that people have at least a basic understanding of what that measurement is about. So we've got a graphic here that kind of shows a forest ecosystem, trees and things, and here's a measurement tower located in that forest that's measuring vertical wind speed, CO2, and water vapor in this particular example. And we'll see that air is moving up and down into this ecosystem all the time. Warm air is rising up out of the ecosystem, and that will have less CO2 in it because it's been absorbed by the ecosystem. And as that moves out, cool CO2-rich air can come into the ecosystem. And the idea of Eeddy Covariance is to measure the scalar of interest, in this case CO2 and water vapor, and how they are changing with the vertical wind speed. So we've got a brief example of that here in this chart. We've got a couple of minutes worth of data. And you'll see here that we've highlighted on the left some areas that have warm updrafts. This is your vertical wind speed. And so as that's positive, that means the air is moving up. And down here we've got temperatures. So again, warm air is rising, which makes good sense. And along with that warm air rising, we see decreases in CO2 concentration. Then over here we've highlighted a few areas where we've got downdrafts that are cooler, and you'll see higher CO2 concentrations. And so the flux of CO2 just relates to the vertical wind speed and the CO2 concentration and how those come together. So that's the general idea in very basic terms behind Eeddy Covariance. And now we want to show you some data that's been collected with the 7700 methane analyzer. The same ideas apply, but now the scalar is methane instead. And I'm going to start with an example that's from a very brief period of time, just 60 seconds. And these data were collected in Baja, California, in a Pacific mangrove forest. And what we're looking at here is 10 Hertz data that was collected with the LI-7700 and also with a sonic anemometer. So we've got vertical wind speed as well as methane. And we also had an LI-7500 at the site that was measuring CO2 and water vapor. So about an hour and a half after sunrise, when the mangrove ecosystem is just kind of getting going for the day, it's taking up CO2 from the atmosphere and it's releasing methane. And so what we see in this top chart is as the vertical wind speed goes up, so does methane concentration. So those are correlated together positively. Now here in the middle, though, we see as the vertical wind speed goes up, CO2 concentration goes down. So there's a great example that shows how the ecosystem is currently a sink for CO2. But down here, when we look at the comparison between methane and CO2, we see that they're anti-correlated because the ecosystem is a source for methane and a sink for CO2. So that's just kind of an example of the kind of data that you'd collect with this instrument. Extending our time frame out, now I've got a few months worth of data here in this plot. And what we're looking at here is the red lines are absolute methane concentrations measured with the LI-7700. The green lines are calculated methane fluxes from the ecosystem, and the yellow line is air temperature. And this data was collected in a sawgrass wetland in Florida in the Everglades. And again, we used the LI-7700, and there was also an LI-7500 at this site as well. And what we see here that's interesting is that methane fluxes are correlated very closely to air temperatures. And so again, you'd kind of expect that as temperature increases and things get warmer in the soil and the microbes are more active, we see higher concentrations of methane coming out of the soil, and we see positive methane fluxes from the ecosystem. So that's again an example from mid-November through mid-January. You may notice that there's a small gap in the middle of the data set, and that's because we had some difficulty with our ancillary equipment. One of our solar panels broke down, and so we had a small gap there where we had to get out in the field and fix the solar panel system. The next group that I'm going to show you is similar. It's the same methane concentrations on top, but now we're looking at methane concentration in relation to wind speed. And as we look here, we'll actually bring in some lines that show areas where methane concentration is peaking, and those correlate to times when wind speed is decreased. And that's going to happen because as wind speed slows down, methane is increasing because it's coming out of the soil, because the system is a source for methane, not a sink. So as wind decreases, absolute ambient concentration increases. And these are the kind of interesting observations that you can't make unless you have high-speed continuous data sets. In systems where we're only collecting samples every week or two, with chambers to go back and analyze in a lab, we just can't see the kind of resolution that we get here. And this kind of data really helps us to get a much more clear picture of what's happening in ecosystems. And it's an important advantage to using gas analyzers that are meant for field deployment instead of going out and collecting those individual discrete samples. So that gives you some kind of a sense for the kinds of data that we're collecting with the instrument, and why it's important to have a field deployed instrument that can be out there making high-speed measurements at a regular basis. For more information about the Eeddy Covariance method, if you're interested in understanding that more clearly, LI-COR has put together an online tutorial that explains the Eeddy Covariance method in detail. It starts at the beginning, goes through the basic theory, goes through instrumentation requirements and calculation methodology, and gives you a very clear understanding of what Eeddy Covariance is about. Our scientists put quite a bit of time and effort into preparing that, and it's available for free on our website. So I'd encourage you to go take a look at that at LI-COR.com. We're going to shift gears now and talk a little bit more about the LI7700 analyzer itself and some of the advantages that we see for using this instrument for Eeddy Covariance fluxes. As I've mentioned throughout the talk, this instrument was really designed for remote field deployment, and that's important because to make these measurements, we really need to be in areas where methane fluxes are interesting. Those areas tend to have limited access to infrastructure. So low power consumption and being capable of making the full complete measurement with solar panels is really important to an instrument for these kinds of measurements. The LI7700 is a self-cleaning analyzer. It's got an ability to clean its own optics, and I'm going to explain that more here too. But self-cleaning instruments are going to be much easier to deploy in remote sites because you're not going to have to visit them as frequently to keep the instrument running properly. The LI7700 is weatherproof, so it is designed to go out and be left out 12 months a year in very harsh environments and continue to collect data. And we do have an option for data logging with the LI7550 analyzer interface unit. The instrument was also designed for Eeddy Covariance, so it's a very high-speed measurement, as we've already mentioned. Bandwidths are selectable at up to 40 Hertz. Definitely very doable for 10 Hertz and 20 Hertz, which would be more traditional for Eeddy Covariance measurements. Being an open path instrument, it's by nature an in-situ measurement, so we're not requiring pumps. We're not pulling air samples down meters of tubing to get from the sample site to the analyzing site, and we're not then dealing with tube attenuation and problems like that either. And the instrument does have analog inputs for sonic anemometers or for ancillary sensors, because we know when you're making an Eeddy Covariance measurement, there's a lot of things that all have to come together at once to make a good measurement, and this instrument was designed with those things in mind. I mentioned low power earlier, and the fact that typically places where methane is really interesting are not places where we have good access to power. And this map is a composite that we put together here that has data from NASA, NOAA, and also the Skimmicky group. And what we're looking at is just a map of the world, obviously, and the white areas have access to grid power. Those are areas of the world where you can readily access mainline power to run instrumentation. Now the areas that are green and purple and kind of yellow, those are the areas where there's either sources or sinks of methane. There are fluxes that are interesting in these areas. And unfortunately, what you'll notice is that those areas don't tend to overlap. Methane concentrations are changing and fluxes are occurring in areas that tend to be remote, just by the nature of the ecosystems that are active in methane. So having an instrument that you can take out into a remote area and operate effectively is going to be really key to being able to get where the measurement of interest is. And just to show you an example of that, this is a picture of a field station in the Everglades in Florida. And this Eeddy Covariance tower is operating the LI7700. It's also operating an LI7500A and another CO2 analyzer that we were testing at the time, the LI7200. It's got full meteorological equipment as well and a sonic anemometer for the flux measurements. This entire tower is running off of this solar panel system right here and these batteries. So there's no need for any kind of external infrastructure to be able to deploy this tower and make these measurements. The LI7700 requires 8 watts of power during normal operation. When you clean the mirrors, which we'll talk about more in just a minute, you add about 8 watts of power consumption, but only during the cleaning cycle, which is usually about 30 seconds. So for brief periods, you'll need just a little bit more power to operate the instrument. And if you're in an environment where there's high condensation and condensing conditions, you can also operate mirror heaters to keep the mirrors at ambient temperature so they're not condensing. And those heaters can add a little bit of power consumption as well, possibly up to 7 watts, just during the period where they're cycling and keeping condensation down. Now, here's an image of an instrument deployed over a cornfield. And it's deployed in conjunction with an LI-7500A. And I just want to use this to point out some of the key points about the LI-7700. As I mentioned earlier, there are heated mirrors. So both the top mirror and the lower mirror are heated, but they're not adding energy to the system much. They're just keeping the temperature of the mirror slightly above ambient, so those mirrors don't become places for water to condense. This lower mirror is actually spinnable, and we do that so that we can clean the optics, and I'll get to that in just a moment. I'll explain how that works, but that allows us to operate this open path instrument in real-world environments like cornfields or wetlands or Arctic areas. And when the instrument senses that deposition is occurring or that the optics are getting dirty, it cleans itself, so you don't have to be on the site monitoring the instrument performance and cleaning the optics regularly. There's an air temperature thermocouple very near to the optical path. As I mentioned earlier, we use that to measure temperature and make compensation as needed. This is a radiation shield on top of the instrument. This keeps us from condensing as much on the top mirror, and it allows us to run the heaters less. So it's a power-saving technique that we found that will help us keep condensation-free optics without having to dump extra power into keeping the mirrors heated. Now, the instrument also has Ethernet output, so you can send data directly out from the instrument to either a data logging device or to a network, so you can access the instrument remotely. If you have a networked site, you can just sit at your desk, pull up the instrument, make sure it's operating properly. You can also collect data over the network, either directly from the instrument itself, or if you're using our logging device, you can connect and pull data files across from that logger. This is a shot of the analog input ports that you can use to again integrate your sonic data directly with your methane measurements. Something that's not shown in this picture because it's lower on the tower is the LI-7500 analyzer interface unit, and that's the point where we actually do data logging and different data output options. So first I want to explain the washer assembly a little bit more. We've talked about that briefly, but the way this works is we zoomed in here on this image and we're showing a nozzle that's attached to one of the spars of the optical path. And that nozzle is connected to a fluid reservoir that's mounted to the tower. And periodically, again, the instrument will monitor its signal strength. And it'll do that as often as you'd like. And it'll watch that signal strength. And there's a software parameter that you can use to set a threshold. And you can monitor signal strength such that when the signal strength degrades below that threshold, this washer turns on and cleans the optics. So the way that works is you'll see the mirror here just stationary with the nozzle beside it. When it's time to clean the optics, this mirror begins to spin. And it spins, there's a motor underneath it that spins the mirror at a very high rate, about 5,000 RPM. And once that mirror is spinning, then the nozzle begins to apply a cleaning solution. And so we're spinning and cleaning this mirror for a period of, like I said earlier, maybe 20 or 30 seconds. And then the pump shuts off. The mirror continues to spin until it's dried itself off, and then it comes to rest, and you continue making measurements. So this is a fully automated system that allows you to keep the instrument running in the field for longer periods of time. And again, you can set this up so that it only checks and washes between 30-minute averages if you want. So if you are making Eddie covariance measurements, you obviously don't want this to happen in the middle of your 30-minute averages. So you can set this up to only check and clean itself as needed between your 30-minute measurement averages. This next image is just giving you an idea of the instrument performance related to mirror cleanliness. Because as I mentioned earlier, instruments that you may be familiar with for measuring methane at high frequencies are going to require very high reflectivity optics. And if anything gets in that optical path, you're going to lose your signal. But with the LI-7700 and the WMS technology that we're using, the way we've designed our optics, you'll see that our signal strength, which is represented by this RSSI number, can be anywhere from 90% all the way down to about 10% before we start to see signal degrade. So there's a wide range of cleanliness that will still provide a really good methane concentration and a low noise signal. So that's just an idea of how well the instrument performs in the field.
Bill, I'm going to stop you for a second here. We've been getting a lot of questions in. Our panelists have been very busy answering everyone. But I have a question from Corolla that I think is appropriate for you to stop and answer quickly for everyone to hear. She asks, how often do you need to clean the optics, and how often do I need to visit the site to refill the reservoir?
Okay, thanks, Ashley. That's a good question. We'll go ahead and clarify that a little bit more. Corolla, the first part of your question was how often do you need to clean the optics, and it really is going to depend on the location where the instrument is operating. There's going to be some ecosystems that just have more dust and pollen and deposition hitting that mirror than others. We've operated these instruments in a lot of different places around the world, North Alaska, in the Arctic, to Everglades in Florida, and even to pollinating corn in the Midwest in the United States here. So it's really going to depend. But just as a point of reference, we did operate the instrument, as I said, in a pollinating corn condition here in Nebraska for a while, and we were able to only have to run the washer maybe every few hours. So it doesn't happen too regularly, but it will depend on the site. And then the second part of that question ties in well. How often do you have to fill the reservoir? The reservoir that I showed you has a 4-liter capacity, and if you run your cleaning cycles for about 20 or 30 seconds at a time, that reservoir will give you about 20 or 30 cleaning cycles. So again, depending on how often you have to clean, if you're cleaning the instrument maybe once a day or twice a day, you're going to be able to use that reservoir for quite a few days. You can also attach the pump to an external reservoir. So if you've got a site that's really difficult to get to, and you really don't want to have to get out there very often, or there's just a lot in the air and you have to clean more frequently, you can just attach any liquid reservoir and fill that up and use that as well. And I should have mentioned the cleaning fluid that we're using is just very basic. It's just a mixture of water and alcohol so it doesn't freeze. You can use automotive windshield washer fluid. We use that at sites as well. So it's very flexible. There's nothing special that you need to look for in a cleaning fluid or anything like that. And like I said, the frequency that you're going to have to change or add fluid to the reservoir just kind of depends on the environment you're in. Something I should mention, though, is that there will be times that you do have to go to the site and actually wipe off the mirrors. The way the optics are designed, they keep themselves clean for a while, but there will be times that you need to actually wipe them off. Again, we designed this open path instrument with optics that are very scratch resistant and very durable, so you're not going to have to use special optical cleaning equipment or soft cloths or things like that. You can just go out with any kind of a standard cloth or a shirt or anything else and just wipe off those mirrors. But what we've seen in the field is that at a worst case, probably every 2 or 3 weeks you may have to go out to the site to clean off the mirrors, but more likely it would be 4 to 6 weeks between field visits. So thanks for your question. That was a good one, and we'll go ahead and move on now and talk a little bit more about the LI-7550, which I mentioned earlier. That's the optional analyzer interface unit that interfaces with the instrument to provide a variety of benefits. If you're working at a site that doesn't already have instrumentation in place for logging data, the LI-7550 does have high-speed USB data logging, so you can use it to collect data at very high speeds from a variety of sensors and log all that in a merged file that's time-stamped. It also has additional analog inputs, so if you've got multiple sensors that you want to interface with the methane data, you can use the 7550 to provide additional inputs. And it gives flexibility to your outputs as well. With the 7550, you can send data out on Ethernet lines, analog signals. If you're working with Campbell Scientific data loggers, you can use an SDM interface, and you can also use a standard serial interface. So there's a lot of flexibility with the LI-7550 analyzer interface unit that you may or may not feel like you need to take advantage of at your site. We just want to give people opportunities to get things working as easily as possible. And these next images show a couple of configuration options that would show how you would actually hook pieces together. You'll see here an example of a sonic anemometer, which you can connect analog signals directly into your LI7700 instrument head. And then you can send that merged data stream out of the 7700 via the Ethernet line. You can either connect that to a laptop on site or to the network if you have a networked site. And there are also certain data loggers that will accept Ethernet signals as well. So again, there's flexibility there to just go straight from the instrument to a data logging device. You can also work with the LI7550, which again will give you just additional flexibility to input more channels and then to output those data to a laptop, to the network, or to a data logger in different ways. So that's really the purpose of the 7550 in this instrument configuration, is just to give you flexibility that you may need to get your system running. System integration is really important, an important piece of the design of the 7700. You know, if there's sites that you already have where you're measuring CO2 and water vapor fluxes and you want to add methane, it's very easy to integrate the 7700 into existing sites. And if you've got areas that you want to set up brand new monitoring sites, LI-COR's put together some packages of instruments, greenhouse gas packages that provide methane, CO2, and water vapor analyzers. They provide inputs for sonic anemometers and options for data output or data logging. So LI-COR has really tried to bring together the instrumentation that people need to make these measurements and be able to get that put together easily. Next, I want to just address a question that I'm sure has come up with some of you, and it's something that I hear a lot when I'm talking about this instrument, and that's the question of, well, the instrument looks neat, it looks great, I appreciate the open path design, but it's just so big. Does it operate well being that large, or does the size impact the ability to measure fluxes? And that's an important question, one that, like I said, I'm sure many of you are wondering about, and one that we like to address head on, because the instrument does perform very well in the field, and it does a great job of catching the high frequency fluctuations that you need to catch to make a good Eeddy covariance measurement. And to test that, we've collected data and we've plotted instrument co-spectra. And so these will be familiar plots to many of you who've worked with Eeddy covariance in the past. You'll see these co-spectral plots. And first we want to show you a plot at 2 meters above the canopy. So that's a standard flux tower height, 2 meters. And you'll see here we've got a line that represents the theoretical ideal co-spectral line. And then we've got a methane flux, which is measured with or shown with the red dots. And we've got CO2 with the green squares, and water with the blue triangles. And you'll see here that in the Arctic tundra, in a wetland in Alaska, at 2 meters above the canopy, we get very good correlation in the co-spectra response from the methane analyzer and the CO2 analyzer. And the CO2 analyzer in this case was the LI-7500. You'll see that at a 4 meter height here in this plot, we collected these data in a sawgrass wetland in Florida, and you'll see the modeled response. Then you'll see the methane analyzer response and the sonic sensible heat flux, which is many times used as kind of a standard to compare against. And you'll see at this high frequency end, there's a little bit of data loss, a little bit of frequency loss, but not very much. I mean, it's a very manageable amount. And here at a 7 meter height, we've got another plot from a mangrove forest in Mexico, and again you'll see kind of the ideal line shape. You'll see line shape from a closed path analyzer here as well. And then you'll see methane fluxes CO2 and water vapor fluxes. And again, you'll see the drop-off at the high frequency for the methane analyzer is very comparable to the drop-off in the 7500. So as surprising as it seems, really you don't lose any more high-frequency fluxes with the 7700 than you do with the 7500, and that's been very encouraging for us. We've measured this even down to 0.75 meters above the canopy, and at that point you certainly do see a more significant drop-off of the high-frequency fluctuations, which is expected, and it's very atypical for a person to try to put up a flux tower that close to the canopy anyway. But just so you know, I mean, there is a point where you do see more significant drop-off, and you need to watch that. But for standard flux tower heights, 2 meters or higher, we get good co-spectral response from the instrument. So hopefully that'll clear up some questions as well. And with that, I think that's all that we had for the formal presentation, and now we can go ahead and address any questions that Ashley might have that we want to let the whole group hear.
All right, I've pulled a few questions here. The first question I have is from Tatiana, and she asks, how stable is the instrument over time?
Okay, Tatiana, that's a great question. I'm glad you asked about that. Because it is a new instrument, we've only been collecting data with the LI7700s for a few years now, but we do have some long-term stability data that we can use, and we've certainly had instruments deployed for longer than 6 months at a time, brought them back in and performed factory calibrations and drift checks, and seen no calibration changes at all. So over periods of at least 6 months in field conditions, we've seen absolutely no change in the calibration, and I would expect that number to continue to increase as we just get more data from the field that we can analyze.
Thanks, Bill. The next question I pulled is from Colin, and he asks, how do you position an instrument on a flux tower with other instruments?
Okay, Colin. Yeah, thanks. That's a good practical question. Once you get this instrument, how are you going to get everything connected up together? And I think to answer that, I'm going to go back to an image that I showed earlier. And this is a flux tower that we had deployed again over a cornfield. So you'll see here the kind of the standard instrument bar arm coming off the side of the tower, and we've got the sonic anemometer here positioned in the middle, and it's positioned such that as usual that it's going to disrupt as little of the prevailing winds as possible, so it's positioned that way. Then we've got an LI-7500 here to the side of that in kind of a traditional configuration, very near the sonic path, but again, we'd like the air to go through the sonic first before it hits the analyzer. And now here we've added a methane analyzer to the side, and we've got that analyzer positioned so that the sonic measuring point is near the center of the methane analyzer optical path. And in this case, actually, the methane analyzer could have been closer to the sonic. We just didn't get them as closely positioned as we could have. But you want to make sure, again, that you just try to orient your instrumentation so that the air goes through the sonic first, and so that you minimize the perturbations to kind of the prevailing winds as much as you can.
Great, Bill. Thanks. I think that's going to be our last live question,